So starting again, welcome everyone to the WIN seminar. Today we have Termeh Shafie as our current speaker. And Termeh holds a PhD in statistics. She has been previously worked as a postdoctoral researcher at ETH Zurich in the University of Konstanz, and also in social statistics at the University of Manchester. Her research is mainly focused on the development of statistical methods and models for analyzing multivariate social networks. She loves working interdisciplinary and doing research that moves across scientific borders. As such, she has created an R package in which novel statistical network analytics tools are implemented and made accessible for fellow researchers to use. So sorry about that. This is not my first language, but I'm really happy to have you all here, and we are going to have Termeh doing the presentation, and then we are going to have some time for questions and everything. So if you want, you can also pop some questions in the chat. I'm going to be looking at it, but for sure, we are going to have a time for just talking later on. So thank you, Termeh, for being here.
Well, thank you for having me, and thank you for that very nice presentation. So I'm going to try to share my screen. Can everybody see my screen now?
Perfect.
Perfect, excellent. So yes, thank you again for that nice introduction and for allowing me to speak in this seminar, which I think is an amazing concept. So my talk is going to be about one of these examples that Francesca mentioned, that I like to work in method development. And it's going to be about statistical entropy analysis of network data. And the comic that you see on this first title slide is a comic I use a lot. It's always there when I'm talking about entropies. And I really identify myself with the woman, or the mother in this case, probably in the comic, because as soon as something goes up and people come up to me and say, okay, how do we statistically analyze this? Or what do we do to analyze this network data? Well, my go-to answer is, entropies. And I hope to show you why that is the case with this presentation. And I have, I'm going to start off with just giving you a little bit of background to how I came to work with statistical entropies. So the reason for that is I'm mainly interested in working with multivariate network data, or social network data in particular. And in multivariate network data, what you have is a lot of node attributes, and you have a lot of different types of ties. So the node attributes is what we refer to as exogenous variables or composition. And they may be measured on different scales. So you might have things like age, which are numerical, and then you might have nominal scale, which could be anything that could be from eye color to political interest or political ideology. And you may then, of course, also have this interplay of composition, the node attributes to the structure. So this is what's interesting. So the arrows here indicate that we are interested in this interplay that goes on between composition and structure. And structural features are the different types of ties that exist in the network. Now that could be undirected, directed, weighted, signed, any type of tie that might be of interest for that network data that you are working with. And understanding the interplay between these two things, structural and composition, well, you need to understand the interdependence, which is sort of the key word when you are working statistically with network data, that, observations, especially dyadic observations, are interdependent. So you need to sort of assess the interdependence between composition and structure. And the ways you can go about doing this is a few examples are given here. This is not an exclusive list, of course, but just to give you an idea. So you can use informative dyads and triads or higher order configurations. You can explore the data to inspire further investigation, identify social phenomena and processes. So you want to understand why people connect in the way that they do. So are the node attributes actually playing a role in how people decide to connect with each other? And you want to specify, of course, various types of models, multiplex, multi-level, or any other types that you might be interested in. Now, the problem with working with multivariate network data is the fact that we have variables measured on different types of scales. So you may have numerical, you may have nominal, you may have ordinal. And in particular, when you want to, for example, if we just focus on nominal scale variable, that's sort of a challenge in statistics, generally speaking, because you cannot calculate mean on a nominal scale variable. So nominal scale variable is, for example, let's say eye color. So you have brown, green, and blue. So you cannot calculate the mean in your data set, what the mean is of eye color. So just as an example of how sort of that's a challenge if you have these kind of scaled variables. So measures of, you know, centrality or spread and flatness, association, these kind of things are needed to sort of include these types of variables in the analysis as well. And that's where information theory comes in, because that sort of provides us with the tools that you can use to analyze a whole bunch of different types of variables that you have, including ordinal and nominal scale variables. So multivariate statistical entropies are used to find, for example, redundancies, conditional dependencies, functional dependencies, and so forth. And I'm going to show that in this presentation with a lot of examples. And as was mentioned during the introduction, I like developing these kind of things in R, the statistical software R. And I have developed a package called Entropy, which is published on CRAN, so you can download it if you're interested. And I will show you plenty of examples in R. So as we go on, we talk about different concepts that you can use to analyze your network data. I will try to give you a few examples of how you would actually get those results from R. In the package, we have I have implemented the internal data set. It's a very well-known data set from Emmanuel Lazega. So it's a data set of lawyers from a law firm in the US. And what we have in this data set is different types of relations moving between the lawyers in the firm. We have undirected co-work, so who works with who. We have directed advice, and we have directed friendship networks. So people name who they consider their friends or who they go to for advice. The attributes that we have are all listed here. So formal status is whether you are a partner or an associate in the law firm. And we have gender, we have office location, which are 3 different locations, years with the firm, age of the lawyer, what kind of law they practice, for example, litigation or, oh, well, it's actually only 2 outcomes there, it's litigation or corporate. And then 3 locations where we have which law school they attended. So I'm going to use this data set as a running example in this presentation, and I will have little sort of these code snippets to show you how you call the functions in the package and how you basically call different functions to do the analysis for you, basically. So the key thing about working with entropy analysis is that you need to define your variables correctly. So when you're working with network data, it's important that you focus on a specific variable domain. And what that means is that you could, of course, have variables on different domains. So you could be just focusing on the node attributes, or what we call the vertex variables, but you could be interested in dyad variables, or you could be interested in the triad variables. So what you need to do is to specify these variables which are observed and transform them into the domain of interest. So I'm going to give you an example of what I mean with this. So for example, we had a whole bunch of attributes observed on the network data that I showed you in the previous slide. And if you look at gender, for example, it's a binary vertex variable that you have observed. You've observed the gender of the lawyers in question. But what you can do is that you can transform these into dyad variables. And you do that by just summing up the attribute values of the sort of incident vertices. So whether you have 1 or 0, and that would lead to a trinary dyad variable. So you will have 3 different outcomes on a dyad variable, which is gender. So this way you can sort of decide that you want to perform the analysis on the vertex variables, dyad variables. You could even create triad variables, as I will show you. So the other way around you could also work. So you might have observed a dyad variable. So for example, say that we have this co-work relationship that we have, people, which lawyer co-works with another one. But what we can do is that we aggregate this variable into a vertex variable if we are interested in analyzing vertex variables. So what we do then is that we can, for example, compute the degrees or use another centrality index. And then what we do is that we categorize the outcomes of that, and we sort of get a vertex variable that could have high or low degree, for example, if you only have two different outcomes on that variable. So in this data set that so when you're working with sort of data sets, you might want to be interested in deciding whether you want to work with dyad or triad sequences. And I'm going to give you an example. So the thing with entropy analysis is, as I would go on, is that the values actually don't matter. So the numerical outcomes don't matter. What actually matters are the frequencies of occurrences. So if you have two variables and certain outcomes seem to appear together very frequently, well, that means that there is a clear pattern going on between those two variables. So because they are appearing together, there might be some form of an association between the two. So when you're working with dyad sequences, what you can do, so you have a dyad here, UV, two nodes, and you can create a dyad sequence saying, for example, okay, if I have a node variable that is has binary outcome, say that this one has 1 and this one has 0, we have an undirected tie between them, but we don't have a tie 0 going from U to V, but we do have one from V to U. So you create these sequences that you can work with, and these sequences will have a finite space of outcomes, so you know how many possible outcomes that exist because of the zeros and ones that exist in this dyad sequence. Or if you have 3 outcomes, that's the same. You can have 0, 1, 2 then, or even more, 0, 1, 2, 3, 4. You just have to be careful so that you don't create sequences that have many possible outcomes in comparison to the number of observations that you have, because obviously if you have the longer sequence you have, the more outcomes are possible, and you have to make sure you have enough observations to sort of work with the data, so to say. So triad sequences, the idea is sort of the same. So it's a little bit longer sequence that you can work with. So you will have one for the node attributes, one variable for the node attributes. You have undirected relations and you have directed relations, and then it just gets a little bit messy because you have to consider 3 variables and how things move. But if you look at an example, it's hopefully clear. Here we have an example where the node attribute actually has 3 possible outcomes. And this is what we have observed. So we have 3 different colors, and then we have 3 different ties. So the undirected tie seems to move everywhere. So we put 1, 1, 1, and then we put 1 and 0 for what we have directed ties as well. Now, this is just shown for one node attribute, one undirected relation, and one directed relation. So the question is, of course, well, you know, you were talking about multivariate data set. How do you put that in? Well, how you put that is simple, by just indexing as many as you have. So you could keep working with this sequence and making it longer depending on how many node attributes you have. So here's 2, for example. And then you just index on with the number of undirected ties you have, or number of directed ties you have, and so forth. So these are sort of the variables that you will be working with. Now, in the network study that we have, that I'm using as an example in this presentation, if we look at the network data that we have different types of variables. Of course, we have 71 lawyers observed them. If you look at vertex variables, that means that you have 71 observations. If you decide to look at the dyad variables, that means that you will have about 2,500, because it means the number of pairs of nodes you can take out of these 71 nodes. And if you decide to look at triads, well, then the number of observations is almost 50, well, it's over 57,000. So it really all depends on what you want to work with. So again, what you can do is observe vertex variables into dyad variables. You could actually even create new dyad variables. So for example, we have a friendship network, which is directed. You might want to be interested in looking at a friendship network that is undirected, meaning that you could just look at those that mention each other, so mutual friendship. So that could be sort of a new variable that you create yourself. And everything that you have observed, vertex variables and dyad variables, can be transformed into triad variables. I'm going to give you an example now how you can actually work with this. So you have the data frame of the attributes from this data set in R, and what you can do is that you can look at the data frame of observed and categorized node variables, which would look like this. So these are just the 5 first rows. And please note that years and age, what I've done here is, you can see in this code snippet here, Years and age are two variables that I categorize. So what I do is that I take the sort of the value that we have at hand, and I use the median to split if we have those who spent a lot of years at the firm and those who spent fewer years at the firm. What is important here for the sake of the entropy analysis is that you try to, why I use the median as well, is because you want to create equally sized groups to make it sort of so that the results don't get skewed that way. So as you can see, these are the attributes that we have. So these are sort of the vertex variables that you can choose to work with. You can also work with dyad variables and triad variables. And I have two functions implemented in the package called getDyadVar and getTriadVar. And what you can do with those is that you basically put in one variable. So I could put in gender here, and then I write that it's an attribute because it could, of course, also be a tie. Then it automatically will create a gender dyad variable, which has a certain number of outcomes, because it will look at, of course, how many, it takes this sort of how many combinations that exist of the node attributes combined into a dyad variable. There will be a message letting you know that you have created a dyad variable with a certain number of outcomes. So it's quite straightforward. Similarly, you can create triad variables using this function instead. And the thing with triad variables is that you get a lot of possible outcomes. I think it's about 64 in this case. So you get 64 possible outcomes. You see here we have the number indicating which outcome we have. So these are, again, basically the dyad sequences and the triad sequences. But because, as I said, we don't really care about the actual values, you can just call them from 1 to 64, the outcomes. It doesn't matter what the sequence actually looks like. So now we want to go to the sort of the million-dollar question: what is entropy actually? And this I found actually on XKCD, and it's about how Shannon with the Shannon entropy, so how the name came about. And I think this is quite accurate even today, because as soon as I sometimes mention entropy, people become quite scared and just walk back like a scared cat. So I try to show you now what actually entropy is. What I want to make very clear is that we're not talking about entropy in the context of thermodynamics or physics. We're talking about the kind of entropy we use in information theory. And most importantly, we call it statistical entropy because we use it to quantify uncertainty in random variables. And that is basically what statistics is all about, measuring uncertainty. So how you actually calculate entropy is that you have discrete variables that you can calculate based on the frequency of occurrences, what's going on in the variable. This is the expression. We use logarithm to the base of 2 because we are working with bits, binary digits. So it's about that comes from information theory, because you want to see how many bits is required to store a certain word, or a code word as they call it in information theory. The idea here is the same. So what we want to do is that we want to understand how much of an element of a surprise you have in a random variable based on the outcomes that you get. So if you get minimal zero entropy, it means that this variable, this random variable, which maybe say it's, for example, you have your observation and this is gender in your, the variable gender. If you get that you have zero entropy, it means that you have no uncertainty in this variable. So it actually means that you have observed, for example, only females in your data set. So there is no variation at all. However, if you look at the possible outcomes that you have on this random variable and take logarithm to the basis of 2, that means that you have maximum entropy. So you have basically full randomness in your data. And I have actually an example to show you. So instead of thinking about gender, let's think about flipping a coin. Now, if I flip a coin, say 100 times, and say that I get 50 heads and 50 tails, but that means that it's very unclear what's going to happen the next time I flip the coin, because I got equal amounts of heads and tails. So that's when I have the biggest number of element of surprise, if you want to call it that. If I instead, for example, flip a coin 100 times and I get 80 times heads and 20 times tails, well, in my head, I'm thinking, rationally speaking, it's more likely that I get heads because I seem to get it more often. So there's something wrong with the coin, probably. That means that the entropy is probably a bit lower for that case, because I'm more certain what's going to happen in the next step if I flip it one more time. So if you would actually visualize the entropy of a binary variable, for example, flipping a coin, it would look like this, the function. So you will see that maximum entropy you get when you take logarithm to the basis of 2. And it's when the probability, or the relative frequency, if you want to call it that, is equal to 0.5, because that's when you are most uncertain what is going to happen next. And that's when you have the highest element of surprise, if you want to call it that. This is what a univariate entropy is. Now, more interesting is, of course, when you move on to bivariate and higher order entropies. Now, when you're working with 2 random variables, it's a very similar formula to calculate the bivariate entropy. And it is bounded according to this inequality. And why I have included this inequality is because you will have equality to the left. So the univariate entropy is equal to the bivariate entropy only if you have a functional dependency between x and y. What does that mean? That means that every outcome of x yields an outcome of y, basically. On the other hand, you will have equality here, so that the bivariate is equal to the sum of the univariate entropies. You will have this case only if x is completely independent of y. So the 2 increments that we have around this inequality, around the bivariate entropy, is what we call the joint entropy. So it's the amount of mutual information that we have in the data that you are working with these random variables. And it's equal to 0 if you have that these 2 variables are completely independent of each other. Similarly, you can calculate what is called expected conditional entropy. And that gives you a value that you can interpret as how strong the prediction is to explain y using x, meaning how good of a prediction do I get if I use one of the variables to explain the other one, so the functional dependence between the 2. So to summarize what you can use these things for, bivariate entropy, as I will show you, is a very useful tool to perform, if you want to call it dimensionality reduction, or variable selection, or variable screening, because you can find out which variables are redundant. For example, if you calculate bivariate entropy and it's equal to the univariate entropy of one of the variables, that means that you have the same amount of information. So you will get the same amount of information using one variable as 2 variables. So one of the variables is obviously redundant and you can exclude it from your analysis. And use expected conditional entropy to create prediction power that I will show you as we go on. So the idea to higher order entropies is very similar, so I'm not going to spend too much time here talking about it. So basically what you do then is that you calculate expected entropy, and you can calculate expected conditional entropy. That means you want to explain z using pairs of variables, and that gives you an idea of how good prediction you get of this 3rd variable using the other 2. How do we calculate these values now? Well, in the functions that you can use in R, there is a function called entropy bvar that will give you a matrix of the variables that you have in your data frame. And you will see that, so basically you see what the bivariate entropy between row and column variables is equal to. So for example, gender and office have a value of 1.93. The value in the diagonal is the univariate entropy that you get. So you automatically get these values out as well. Now, if you remember what I was talking about redundancy, now this variable senior, it's not surprising at all that it is redundant, because if you look at this variable in the data set, you will see that it's just a sort of an variable going from 1 to 71, because 1 has been is the most senior in the law firm, and the second one is the second most senior, and so forth. So it has a unique value for every observation, and so there's really no information there to use in your analysis. So it's not surprising that it comes out as redundancy or redundant. So, but I've included it here just to show you how you can use it in your analysis. I also have implemented a function called redundancy. And that means that you can use this one directly, and what you get then instead is just a matrix of 1s and 0s, and you will get a 1 wherever you will have redundancy in your data frame. So you get a great overview of where you have these kind of redundancies in your data set. If you do not have any redundancy, there will be a message letting you know that there are no redundant variables in your data set. Please note though that if you decide the decimal here is sort of the rounding figures, Obviously, if you round to, the more you round, the more redundant you find because the values become almost equal. Joint entropy, there's a function for that called joint entropy, and what you get as an output there is a matrix. So similarly as the bivariate entropies, you can see what the joint entropies between pairs of variables is equal to. The diagonal again is given as the univariate entropy. And also note that the example I have here now is for the dyad variables, and previously it was for the vertex variables. That's why the diagonal is of course not the same here. So what you get is this matrix letting you know what the value is equal to, but what you also get is a table letting you know the frequency, the unique values of the entropies, joint entropy that you have calculated. So you get a table that looks like this. So you will see the joint entropy here, how many times it appears, and how many values you have greater than that. And why the third column is of interest is because it will be in the number of ties you will have in what we call the association graph. So I will show you what I mean with that. The way you would read this table is very simple. The first row is obviously where you have the strongest dependence. So remember that the joint entropy or the associations you find is a relative measure. So it's always for the data set at hand. It's not like you can compare it to some generic value. So in this data set, 0.79 turns out to be the strongest dependence that you have. And you can go in and try to find out where you have the strongest dependency, which is between years and status. And that's quite logical. So the more years you have spent at the firm, the more likely it will probably determine what your status is at a firm, whether you are a partner or an associate. On the bottom here, we see that we also have 4 occurrences of the value 0, meaning that we have complete independence between 4 pairs of variables. And you can find these again also in the matrix then, and you will see that we have complete independence between status and the practice, the law practice. You have gender and what kind of law you practice is also independent, and law school and co-work seem to be independent, and gender and co-work are also, and so just gender does not influence who you decide to co-work with, basically who you decide to collaborate with. And I say seem because we are still in a sort of exploratory phase of the data where I cannot conclude that this is deterministic into what we call the divergence goodness of fit test. So you will do proper tests, statistical tests of goodness of fit. Now the association graph, I do have a function called ASOS graph, but for that you will need another package in R, which is called graph, because you're going to visualize a plot. And what you end up is a graph. So it's a different graph than the network you're working with. Familiar with graphical models, this is sort of a graph where you have variables as the nodes, and the ties are basically if there is a dependence between those variables. The cut point here is what determines how many ties you will have in this network. Makes no sense to include everything because everything is connected. Maybe it's not always you will have 0, so it gets very messy quickly. So it makes sense to only look at maybe where you have the strongest association. So if we would choose the threshold of 0.15, you would end up with an association graph with 9 ties. So if you count these ties, they would sum up to 9. So what we see here in the association graph is sort of the associations that we have between components and cliques. And please note that the thickness of the edges indicate how strong that dependency is as well. So we see that the strongest dependency was between status and years, and that's very thick, as you can see here, compared to the other ties. And working with these association graphs allows you to sort of make these tests that you can do. So you can formulate structural models, which I will shortly show you. And you can test these kind of models as well. So to give you an example of such structural models, when you look at this, one model that you might be of interest is looking at this part here that is separate from the rest of the variables, where you can assume that friend, which is not connected to collaboration or co-work, these 2 variables are independent of each other, given advice because there's a path through there. Similarly, you might be interested in looking at whether or not gender is independent of status given years, or because these you have 2 components here, you might be interested in looking if friend, co-work, and advice is independent of the 3 variables here that are very strongly connected to each other: age, years, and status. I'm going to come back to these shortly to show you how you can actually test these structural models. But I wanted to show you also the prediction power or the expected conditional entropy that I showed you before. So you want to find out if I want to predict one variable, how good is this prediction based on pairs of the other variables in my data frame? So there's a function called prediction power. And you can use it very straightforward. You just put in the variable that you want to predict and the data frame that you are working with. And what it does then is that, so for, as an example here, we want to predict status in this data set. Status is predicted here using pairs of the variables. So these are empty now because this is the variable we are predicting. And you can read these variables and try to determine which pairs yield the best prediction, so to say. And how do we interpret that? Well, because we are working with binary digits with bits here and logarithm to the basis of 2, if you round the prediction, the expected conditional entropy, if you round it to the closest integer, if you get a value less than 0.5, that means that you have an unambiguous prediction. So every outcome of X and Y yields an outcome of Z. So that's like a perfect case scenario that you have the perfect prediction. 2 prediction values for Z when you have values between 0.5 and 1 and so forth. So if you have between 1 and 1.5, you will have 4 prediction values and so forth. So if you look at this and read this matrix that you get as an output, you look for the smallest figures, and the smallest figure actually is here. So if you're interested in predicting status, the best prediction you can get using pairs of other variables in the data set is using office, location, and the years that they have spent at the firm. Other good predictors are also highlighted here. So you can see what other examples or other variables that you can choose as well. A very convenient way to do this is also using what I call the prediction power. And this I have done in ggplot. So it's basically a heat map thing you do. So I don't include the codes for this. You can then sort of read just by looking at the colors. The darker colors means that you have the best prediction. And status is the darkest here, of course, because you have a perfect prediction if you use a variable to predict itself. So that's not surprising at all. I also forgot to mention that if you use the univariate, if you want to use just one variable to explain status, that's the diagonal. So if you want to use gender to predict status, that's the values that you get in the diagonal. So that's the values that you get there. So moving on to what I call sort of the more confirmatory analysis that you may want to do of these sort of the data that you have is when we come to what we call the divergence test of goodness of fit. And basically what you do here, they are regular goodness of fit tests if you're familiar with working with them, where you specify a model, and based on that model, you compare it to the empirical distribution that you have in your data to see if you have a good fit between the model that you specified and what you have in what's going on in your data, basically. It's a log likelihood ratio test statistic that you use, which is called a divergence. So you have these two models that you work with, the general model, which is based on empirical distribution, and Q, which you specify. So Q is sort of what you can see as the null. If you want to talk about null and alternative, that's what you specify in the null. And the information divergence is an expected log likelihood ratio, and you can actually show that it's approximately chi-square distributed with a certain number of degrees of freedom, which is the numbers of parameters that you need to estimate these two models, the difference between the two. And this holds for large n. So what we see here is that this is actually kind of the beautiful merger, if you want to call it that, between statistics and information theory, because it follows sort of this large sample of statistics, and it fits quite well with the sort of concepts that come from information theory. I'm going to give you a few examples. Now, you can also specify critical regions with approximately 95% confidence level. The chi-square distribution mean is D, and the variance is 2 times D. And so you can create sort of this, and you only reject for large values, of course. So you get sort of this expression which you can calculate easily, and you can see if your observed statistic value is greater than what you calculate here, the critical value. So I'm going to give you a couple of examples of this. So assume, for example, that you want to see if your variable, you have one variable and you just want to see if it's uniformly distributed, meaning does it have just values, that is 1 divided by this R here. When you do that, well, you can actually simplify so that you know what the statistics look like. I'm not going to go into the sort of nitty-gritty details of this, but you will easily be able to check if you would reject uniformity or not. So can you assume that your variable follows a uniform distribution or not? More interesting is when, of course, you are working with more variables. So if you would go back to the association graphs that we have, assume that we are interested in specifying a model which assumes that X is independent of Y. And so this is just a small example association graph I have made. So here we see that because X and Y has no tie between them, it's reasonable to assume that they might be independent. So you want to actually formally test this and see if you can conclude this, that there is a significant result here. So if you assume this model, what you're assuming is that the probability of these variables is simply the product of the marginal distributions of these variables. And then simply put, the divergence statistic becomes the joint entropy value. So it's very easy to calculate what the statistic is equal to. You have your critical values, and you can easily determine if you would reject or not your specified model of interest. You can also specify conditional independence, as I will show you here. So if you have an example that looks like this, there's a path going to X and Y through Z, then it's reasonable to assume that X and Y are independent conditional of Z. And the divergence statistic then equals the expected joint entropy. So again, it's very straightforward to try to test this and conclude whether or not you have a significant result or not compared to the empirical distribution that you have in your data. You can also make this way more complicated if you like, and do way more complicated model assumptions. So what you can do is sort of what is called a nested model specification. So what we call an nested model specification means that you will basically list different independence and conditional independence assumptions that are nested in each other. And I'm just going to quickly give you a few examples. So assume, for example, that you want to test these two things at the same time. So you first assume that X is independent of all of the other variables. And then among the other variables here, we assume that, sorry, now we jumped. We assume that U is independent of the other 3 variables. And then you can keep going on. You can even include another another independence assumption among the remaining variables, that Z is independent of B given Y. You can do this, and you can test this then by basically summing up the divergence values of each of these independence assumptions that you impose for this specification. Now, this is just recently I implemented the first draft of this function in the package as well. So if you download the package from R, you will not get this function. So you need to then actually download it from my GitHub, where I have sort of development version. So if you want to do, for example, in your data set, friendship is independent of cohort given advice. This was one of the models we were interested in earlier. What you will see is that you can test this using this function I have implemented in Entropy. So you need to install it from GitHub, the development version, and then there's this function. So here you specify the data frame, the 2 variables that you want to use for checking independence, and what you want to condition on. And by default, it's set to null, so there's no conditioning. It currently only works for testing if X is independent of Y, or if X is independent of Y given Z. But I'm trying to make it more general, and so that you can sort of include these sort of nested specifications and so forth. And that's why I have an output that gives you the divergence value, so that as we go on with this function, I can actually include a bit more complicated specifications, and you can easily compare that sort of these nested specification and do the test as well. You get a message when you run the function as well that tells you whether or not you can reject the specified model. So if the specified model, friendship is independent of cohort given advice, cannot be rejected. So it is reasonable to assume that this actually holds. Now, to just sum this up, now I've showed you plenty of examples using the dyad variables. I just want to briefly also mention the triad variables that we have worked with. This is a bit more sort of beautified picture of the association graph. This is not how pretty it comes out from R, but you can of course work with this yourself and make it as pretty as you like. The letters indicate the variables that we have. So we have status, years, age, law school, gender, friendship advice, co-work, and so forth. And the way we worked with this, with these sort of triad variables, is that we asked ourselves these kind of questions. Okay, we started assuming that we can just run a dyad independence model to explain triadic behavior. So how do people connect in threes, basically? And what we found out, not surprisingly, that it's not sufficient to explain that, because, you know, it's social networks and there are so many dependencies in there that we don't even want to, you don't know where to start usually. So the next question we asked was, can attributes of adjacent vertices explain dyadic dependence? And to address that, we decided to fit block models. So you assume, so you block the network based on attributes, and you assume dyadic independence within the block, between the blocks. And we use the prediction power plots to basically determine which variable we would block, we would base the blocks on. And this also turns out to be not sufficient to explain triadic behavior. So we went one step further and we said, is there a dependence between the different relations? So we just focused on the different types of relations that exist. And we specified a multiplexity models that turns out to have the almost perfect fit. And this is exactly the same model that we just tested for the dyad variables in the previous slide. So co-work is independent of friendship given advice. And you see this for triadic variables as well. So it's not surprising we have it. So already when you look at the association graphs, you get an indication that this will be probably a good model to specify and test. So I kept talking about we, and I'm going to shortly come to who these we's are. So it's of course not just me working on this. Information-based screening methods for data editing and variable selection should be more accessible and common in applied statistics. So this is sort of the final remarks I want to make with this, that, you know, it should be, it's a bit neglected actually. And I think it's a very flexible and adaptive way to perform both exploratory and confirmatory analysis, and especially if you have variables measured on nominal and ordinal scale. In fact, we are using these methods right now to also perform natural language processing, because when you are doing text analysis, you are working with nominal scale variables. So it's actually a very optimal way to sort of work with that by using these tools. I want to just round off with some references and resources. So this is sort of the paper that introduced this this entropy analysis of network data. It has a few years on its neck, but it provides a very good introduction of many of the concepts I introduced here. And when I was talking about we constantly, I was referring to me and my two co-authors. So we are working on a book, which we are really hoping is going to come out this year and published by Springer Nature. And it's called Statistical Entropy Analysis of Network Data. I also have this package vignettes, which are basically long form guides. So I have written plenty of those so that you can sort of follow them and try things out. The R codes to replicate the examples in this presentations I've made available on my website. So you can in peace go back there and look at those. There's a document there where you can just see all the codes to replicate everything I have done in this presentation as example. And with that, I just want to thank you so much for coming to this talk and listening to this.
Thank you so much, Termeh. I see some claps in the public.
Thank you.
So I'm going to leave your website in the chat so people can go ahead and just look around a little bit, all this interesting stuff. And also I leave your GitHub account, but if you have, for example, maybe the link for the R package in CRAN, do you have it?
Oh yeah, the slides, I have made these slides available also on my website, so you can go there and click to these links if you want. So it's everything should be available there.
That's amazing. Thank you so much. So now we have time for question, and I'm already looking at Alice, who already have her hand up. So go ahead.
Hi, Termeh, thank you so much for this talk. I especially liked all of the very detailed examples in the beginning. And so one question that I had specifically about that example where you had something like the rank of seniority or something, and you said, oh, that's a redundant variable. It doesn't have any codependence with any of the other variables that you have. Now that's that's an ordinal variable. So you could think about binning that, for example, right?
Yes,
and
absolutely.
then if you do that, you might end up seeing some codependence, at the very least with age. I would assume that you
Yes.
see some if you do the right binning. So first of all, is that something that you can somehow account for in when you measure redundancy? And if so, is that something that one can do using your Entropy package?
That's an excellent point. When you do binning, you should be you should see some form of dependence arising. I think the binning of this, I'm wondering, let me just think. The important thing is that you do the binning so that you have equal size groups for the sake of the entropy, because if you have different size group, what's going to happen is that you're going to have a skewness in how the frequencies appear. So what you are observing basically. For this variable in particular, now I'm thinking that maybe it will actually not lead to a codependence, because I'm thinking if you have a value between 1 and 71 and you want to create equally sized groups, then you will probably have values that are going to be exactly there's going to be the same number of observations that you call zeros and ones and twos instead, for example. So it might be that you don't see any codependence arising, but I cannot be sure. But that's an excellent point. In the Entropy package, you cannot really do that. So that comes in the sort of pre-step part of data editing. So you have to take your time and bin the data, because in the same way that you would categorize the numerical variables, so that you would make sure that they are classified and have equal size categories as well. And I have a vignette though for the Entropy package, which is called variable domain and adjustments. And there I give plenty of examples on how you would create these sort of categorizations and sort of processing the data before you start the analysis.
Thank you so much. I don't know if anyone else have any questions, comments. I see that Jane, thanks Jane, you mentioned that it's a fascinating talk. Thanks so much.
So if you have troubles, I always try to be very open-minded about getting questions regarding especially the package. So if you're running into problems and analyzing your data and you cannot figure out what to do exactly, please just send me an email and I will get back to you, and I will sort of guide you as well as I can. If it's possible over email. Sometimes it's hard over email when it comes to more technical stuff, but just guiding the analysis is usually possible.
Yeah, I think, Termeh, you can see the chat. I see that Jane also mentioned that it was so fascinating that I can figure out what questions to ask. And I definitely agree with that feeling. But also we have a question from Alice.
A vignette is, I see it now. It's a very good question. It's a sort of a long form guide you write to packages in R. So if you some packages in the statistical software R come with vignettes, meaning you have sort of these long form guides that help you understand what's going on. And what I'm going to do now is I'm just going to try to quickly, if it's possible, go to my, so this is, for example, a vignette. So this I just took now from going to the CRAM page where I have several vignettes, and this is one of the vignettes which is called variable domains and adjustments. And data adjustments. So you will see there is an example of how you would actually perform these sort of categorizations and stuff before you start the analysis. And there are several ones. There's one for joint entropy, there's one for prediction power, there's one for association graphs and so forth. So hopefully this will sort of guide your entropy adventure.
That's amazing. That's a lot of material. So I think everyone has a lot of things to read right now. Perfect. So actually we are at the time, I didn't realize. So maybe we could leave it in there, but so next week we have another WINS seminar. So we are looking forward to all of you, to see all of you again in there. And thank you so much, Termeh, for the whole presentation. It was
thank you for having me.
All the slides were super pretty. So thank you so much for that.
Mission accomplished.
Yes, and leaving all the material available. That's amazing. So thank you so much.
You're so welcome. Thank you again for having me.